So as we introduce Chapter 5, I'm pretty excited about this particular unit. We're going to introduce the concept of a system and systems of equations and how we solve those. We're going to be solving these multiple ways, and we're going to start off with solving by graphing. And I believe that perhaps this is something that you did do a little bit of back in pre-AP 7th grade math last year. So we're going to review that, and then we're also going to add on over the next couple of days, right, some other methods for solving that can be really helpful. Okay, so let's go through and really quickly define, first of all, some of this vocabulary before we get started. So a set of two or more linear equations is called a system of linear equations. A system of linear equations. And there's other systems. A system is any time you have more than one equation, but for our Algebra 1 purposes, we're going to focus on linear equations in particular. So that's what we're working with this year. Okay, so a set of two or more linear equations is what we call a system of linear equations. And then an ordered pair that makes each equation in the system of equations true, right? So that's an ordered pair that works in both. That's what we call the solution. A solution to the system. Okay, so it's really important to understand that it's only going to be a solution to the entire system is if the point works in both or makes both of them true. It's not enough to just have one, but it's only a solution to the entire system if both of them are true when you plug in that x and that y value into all the equations in the system. So that's the first thing we're going to practice, is determining whether an ordered pair is a solution. So in these type of problems, I'm giving you a point, and I want you to determine if it's a solution to the entire system. And again, the criteria for that is that when we input it in the first one, it works, and then we also test the second one and it also works. So it's got to work in both. That's really the big idea here. Okay, so let's start with number 1. In order to determine whether or not that ordered pair is the solution, we're going to test it in each one of those equations. And you don't have to do this, but I like to kind of make myself a little bit of a organizational tool here to kind of keep my work a little bit organized, right? So the first one I'm going to test it in is this top one. So I'm going to test it in that x minus y is equal -2. And what I'm going to do is I'm going to take the ordered pair that we know is an x and a y coordinate, and I'm going to plug them in and see if it makes this equation true, if it works, right? So right now the question is, if we insert a 1 where the x was, so instead of x minus y, I do 1 minus the 3. Does that still equal -2? That's what we're testing for, right? So if I plug in that x and that y, and I solve this, does it equal the -2 that the equation requires? Well, let's see. What is 1 and a -3? Well, it happens to be a -2, so yes, right? That would get something that looks like this, which we know works. So that's, yep, it worked. So yes, that point is a solution in one of the two equations. Well, that's awesome, and that's a great step forward, but that's not enough. For it to be a solution to the whole system, we then have to also test the second one and make sure it also works in that one. So for this one, the 2x plus y is equal to 5. We're going to insert that x and y. So x is going to be 1, the y is still going to be the 3, and does that still equal to 5? That's the question, right? Well, let's find out. 2 times 1 is 2, 2 plus 3, right? So 2 times 1 is 2, and then 2 plus 3 is 5. So 5 does equal 5. So it worked in that one too. So the fact that this ordered pair works in both means that yes, this is a solution to the entire system, right? So it had to pass both tests, okay? And if it passed both tests, now I can conclude, yep, this point is the solution to that system of equations? The answer is yes, because it passed both of those tests. Okay, now let's try number 2. Okay, on number 2, same thing. I have this ordered pair that provides an x and a y coordinate that I'm interested in knowing if it's a solution to the whole system. And so I'm gonna at least make myself a little organizer here real quick. I just like to have it so it's not hard to read, where I can test both equations. Okay, so I'm gonna first test my point in this x plus y equals 4. And that equation right there. Okay, so when I plug it in, the point is 3, 2. So I'm gonna replace the x. For x, I'm gonna plug in a 3. And for y, I'm gonna plug in a 2. And the question is, does that equal 4? Right? That's what we're trying to find out. Well, 3 plus 2 is 5. We wanted this equation to equal 4. Those two things are not equal to each other, right? So when I plug in the 3 and the 2, this gives me a 5. 5 is not equal to 4, okay? So this point is not a solution in the first equation, okay? And that means that it doesn't work for that one. Well, if I want this to be the solution to the whole system, and it fails this first one, y'all, then it's not a solution. That's it. So when it comes to the second equation, the 2x minus y equals 3, I don't even have to test that, okay? There is no need to check here. No need to check, because this point, it already failed, okay? It's got to be a yes for both. So if you test the first one and you see it doesn't work, you're done, okay? You can already conclude, nope, this is not a solution in that system, okay? Now, if you test the first one and it's a yes, you still have to test the second one like we did here. Maybe that one will be a no. If either one of them ends up being no, then that's it. It failed, okay? It's only a yes when both of them work, okay? That's how you determine and check if a point is a solution to the entire system. Okay, so you've got that kind of problem. We're going to leave this one as a quick example in class, so we'll do this one together, or you can do it on your own and then we can check it in class. Let's move on to then actually solving the systems by graphing. So here we already gave you a possible solution and you were just testing it, but here we're actually going to solve a system. Okay, so we use a graph to solve a system of linear equations by trying to find that point that lies on both lines. So that's really the big idea. Okay, we have this system right here, and they've already been nice enough to graph it for us. Okay, that's always good news. And what I want you to remind you is that all of the points on this line are solutions to that line. Like if I picked any of these points, they would work in that equation. Okay, and if I had this guy right here, all of these points are solutions to that one. But then there's this super special point, right, that happens to be on both of those lines, right? And this point is on this line, and this point is also on that line. That's our solution. That is that would, if we plugged it in and tested it like we did up here, would give us yes it works, right? These guys right here would give me yes in one of them but not the other. This one would give me yes in another one but not the first one, you know, possibly, if that makes sense. And then you have other points like this one doesn't work in either one, but then there's this super special point, which is where the lines intersect, that works in both lines, that it lives on both lines at the same time. So the big idea here is when we're solving by graphing is that we are looking for the point of intersection, right? So that's like the big idea behind today's lesson. If you walk out with nothing else, we're looking for the point of intersection when we're solving a system of linear equations. We're looking for the point of intersection. That's our solution, okay? So let's take a look. Let's go ahead and do that. For example, this 3x minus 2y equals 10. If I reorganize the equation and so forth, I realize that this top equation, it's this line right there. And the x plus y equals 0, that's this guy right there. Okay, and the solution, like we said before, is where they intersect. Okay, so we just have to identify what that coordinate is, and that will be our solution. So if we look here, it looks like that point is at x equals 2 and y equals -2. So our solution would be this ordered pair. Okay, solution is always the point of intersection on a system of linear equations. Okay. Let's try this one here. This is a system. They've already graphed it for us. You know, we always start off nice and easy. In a minute, we'll be doing the graphing, but right now they've graphed it for us. And the big idea here is just understanding that once your lines are graphed, your solution is the point where those lines intersect. So if I can identify this point of intersection and find out where that's located, right, that'll be our solution. So this one looks like it's at x equals -1 and y equals -3. So that would be our solution for number 5. Okay, try number 6 on your own and then check it with me. So give yourself a couple of seconds. Okay, and hopefully you understand that the solution is right in here, that point of intersection. And that is located in this particular problem at 4, 2. So those would be the solutions. If we then took this point and plugged it into that equation, we should get a yes. If we took this point and plugged it into that equation, we should also get a yes. It should give us, you know, the green light on both like it did on number 1. So this is if we know the point and testing it. This is from a graph. We know that in a system of equations, we're looking for the point of intersection. Okay. Now they were really nice here. These were nice, easy examples because they had already taken the system and graphed it for us, right? But we know we're going to lead up to where we have to graph our own, right? So here you have kind of just a step-by-step guide to remind you, if that helps, how we're going to do that. And the big thing is graph the equations, and you have a system. There's more than one equation, but the thing is you're going to graph them on the same coordinate plane. Okay, so you're going to graph those on the same coordinate plane. Then you're going to look to see where those intersect and estimate where that point of intersection is located. And then if you're not 100% sure, or you just want to be on the safe side, always very smart, then you can check your point by plugging it in and to the original system like we did on the first few examples. Okay. Now, if your equation is in other forms, you could either go for intercepts or you could, you know, rewrite it in slope-intercept form. So there's standard form, there's slope-intercept. I like both of them. If it looks like slope-intercept like this, just remember the y-intercept always tells you where you're going to begin on the y-axis. Okay? And the slope always tells you the rise and run, how you're going to move. So we always begin at the y-intercept and then we move according to the slope. Okay, so let's practice that. Got my straight edge here. Okay, so if I start off with this equation here, y equals -1x plus 3. I know it doesn't say -1, but hopefully you understand that if there's nothing in front of that x, it's really a -1 there. So if it helps, kind of pluck those out and say, okay, my slope is -1, which is -1 over 1, and my y-intercept is 3. Okay, so to graph that, maybe this will help it if I bring it in a little bit. To graph that, we're going to begin at 3 on the y-axis. We're going to put our point there. Once we are on the y-axis at 3, I know I'm on top of my line. Okay, I'm on the line there. And then I'm going to move according to the slope to get to other points on the line. So if my slope is a -1, which is -1 over 1, that means I'm going to go down 1 and forward 1. Down 1, forward 1. Okay, down 1, forward 1. And I'll generate a good handful of points that I know are correct because they're all on the same straight line. And then I can make my line. So guys, I cannot stress this enough, because you're about to try to identify an intersection. Straight edges, clean lines, long lines are all critical in this process. You cannot just make a short, quick little, segment, because your intersection may be way further out. So make a nice line that really crosses the entire graph. And it's really important that you use a straight edge. Some of you guys are sometimes get a little, excited. Oh, I can do this by hand. On these types of problems, when you're looking for a precise intersection, that's just not going to work for you. You're going to have to make sure you use, and look, it doesn't have to be a ruler. I'm using a Post-it note. It's all good, okay? But anything to make that a really nice, clean, straight line, that's the only way you're going to get an accurate intersection when you graph them, okay? All right, let's try the other equation here. That's one of our lines. This other line, again, y equals x plus 5. If I don't see anything in front of there, I know that's a slope of 1. So our slope for this one is a positive 1, or 1 over 1. And my y-intercept is 5. So that means I'm going to begin at 5 up here, and I have a slope of positive 1 over 1, which means up 1 over 1. Well, that only really gives me the opportunity for 1 point, but I know that a double negative is still the same as a positive. So if I don't have enough room, instead of going up and forward, I could still go down and backward, and I would still be on the same path, down and backward, because a double negative is the same as a positive. So sometimes you can hit the reverse there. And we graph. And then we identify, of course, remember the solution, the reason we're doing all of this is to find and identify the point of intersection. So this is where it's at, right there. That's our point of intersection. And that point right there looks like it is at -1, 4, right? And then to be on the safe side, you could always plug that -1 and 4 as your x and y and see if it makes the equations true like we did on the first two examples. Okay, let's try another one. Let's actually, let's skip number 8. Let's do that one in class. I'm going to mark them, the ones that we're going to do together as a quick review in class tomorrow. Let's go to this one, just because these look a little different. It's a good example to have, okay? So if you graph these equations, this is in standard form. So you either can rewrite it by solving for y. You can move the 3x, divide by -2, and rewrite it in slope-intercept. Or you could use intercepts to graph it. So I'm going to go for intercepts because y'all know I'm a fan of that method. Okay. And so if I just cover this and I do 6 divided by 3, I know that gives me 2. So I know this has an x-intercept of, there it is. If I cover this guy and I do 6 divided by -2, I get -3 as my y-intercept. And that gives me 2 quick points that I can use to graph here. And make your line. So there's my line for the first equation. The second equation just says y equals -3. So hopefully this is already sounding off a little alarm of like, hey, don't forget about those special cases, the horizontal and vertical lines. When we see y equals -3, that's a horizontal line. Ooh, I almost said the wrong thing there. That is a horizontal line at a y-intercept of -3. So that's right here. Okay. So that's the second line. And of course, what are we looking for the solution to the entire system is where they intersect, which is right in here. Okay, so if I identify the location of that point is at 0, -3. Okay, so that's the solution to that system. Solutions. There it is. Okay. All right. Now, I'm going to jump down to number 12. Number 12 isn't a good example of the kind that, even though as much as I like standard form and using intercepts, if I see this is not going to divide nicely, I'm probably going to avoid that. Okay, so you can either use intercepts here or rewrite it in slope-intercept form. Or you could do just some really good estimation, right? So if I do go for intercepts here, when I do 7 divided by 3, you know, when that x-intercept is 7 divided by 3, that's really 2 1/3, right? Then just make sure you're really good about getting a good idea of where that lands. So I'm thinking right about right here. Okay, and then for the y-intercept, that's going to be at 7 over negative 4, and that's going to come out to a negative 1 3/4. So just make sure you're really pretty good about where you think that's going to land right there, and then you can make your line. Or you could solve it for y, but you're still going to end up with some fractions on this one. But I'm just showing you that it's still pretty doable. But this is one where, because things are just slightly off, or just slightly decimals or fractions that you're estimating, it'll be extra important to test this point when you plug it in. Okay, so if you check out the bottom one here, when we do the x-intercept, it's going to be 3 divided by 5. Well, that's the same as 0.6. So on the x-intercept for this, we're looking at about right here. Okay. And then for the y-intercept, it's 3. Y-intercept is at 3 over 2. So that's 1.5. That one's a little bit safer right there. And then hopefully our intersection won't be a terrible decimal. We're about to find out. So when we graph this, it appears to me that this intersection might be landing right about right here at 1, negative 1. But this is what kind of problem I would want to test that on. Okay, so test the point. So we're thinking, I'm going to write it in pencil just to be sure. 1, negative 1 here. And then when we plug that in, let's test it in the first one. If we make x equal 1 and y equals a negative 1, does this equal 7? That's the question. Well, let's see. 3 times 1 is 3. Negative times a negative is a... Does that equal 7? Yes, it does, right? So it passes the first test. Yay! Then let's test it in this other equation. 5. We'll plug in x equals 1 plus 2, and then times a negative 1. And does that equal 3? That's the question. Well, 5 times 1 is 5. 2 times a negative 1 is a negative 2. Is 5 and a negative 2 equal to 3? Why, yes, it is. Ching. See? And so you're able to check both and say, oh, yeah, that point did work. So even though we were kind of estimating these, we did a good enough job that we can say with confidence, yeah, that's our solution. It's at 1, negative 1, right? But that's all about being very precise and careful with your graphing. That's the moral of the story. Okay, let's finish off with one of these word problems, and then we're going to be done. Okay, so let's talk about this first one. It says BK Bed and Breakfast just opened, and it spent $300 to prepare a room to put on Airbnb. Let me adjust that a little bit. There you go. The cost for food and utilities is $15 per night, and they charge $75 per night to rent a room. Okay, so first let's write an equation that just represents their costs. So this is how much they're investing into their business, how much it's costing them. Well, we know that they had to spend $300 to prepare the room, and that it costs them $15 in utilities for every night. Okay, so the $300, that's a one-time investment, but the 15 is every night that they rent the room out. So this would be our equation, where this is the number of nights that they've rented that room out. Okay, this is our cost. This is how much they invested into the room. $300 flat out at the beginning, and then $15 in utilities and such, water, light, internet, for every night that they rent it. Okay, now let's write an equation for revenue, or how much money they make. Well, how much money do they make when they rent it? Sounds like they make $75 per night. Okay, and there's no other fee or anything like that. Basically, every time that they rent the room, it's $75 a night. Okay, so we can take both of those equations and create a system, basically, and then use that to find out some good information here. So how many nights does BK Bed and Breakfast need to rent the room in order to recover their cost? Basically the break-even point, when this is the same as that. Okay, Well, that's basically the intersection of these lines, okay? That's how we're going to decide this. Complete the table below to find out. Okay, so we're just going to basically come up with some values here for this. And we can come up with this table pretty quickly, actually, because we can use calculators now, which is exciting. Okay, so instead of me trying to calculate all these values, I can come to my calculator here. I can go to my y equals if you weren't there already, and I can put in my first equation. 15x plus 300, and I can generate a table of values for that. Okay, so, and then I can fill this in. So this explains to me that if they rented the room 0 nights, their investment would stay at $300. Even then, you know, they did this 300 before they even began to rent it out. After 1 night, it's $315 because it's going to be $15 per night, right? So every extra night is another another $15. So $330, $345, you get the idea here. $360, $375, $390. We're just going up by 15s, or you could just follow along on your table here. Then you've got $405, then $420, then $435, then $450, and then $465. Okay, that's what they would be investing in their room. Now, revenue is what they're making. So if they don't rent the room ever, they make no money whatsoever, right? Okay, and again, you could put this in your calculator if that helps. You could clear this one out and just put 75x. And there, so, but we know that this is increasing by 75 every night. So, you know, if you don't rent it, you don't make any money. If you rent it 1 night, you make $75. 2 nights, $150. 3 nights is going to be $225. And then 4 nights, $300. And 5 nights, $75 right there. Okay, and then 6 nights is $450, and you see it's just increasing by that $75 for every night that they have it rented out. And then 675, 750, and 825. So that gives you some good values up to 11 nights, and the pattern would continue. But what we wanted to know was this break-even point, right? When would the cost and the revenue be the same? Because as you can see, starting off, the money they're investing for a good while here is way more than what they've earned. So how far do they have to go until they basically recover their expenses? Ding, 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 ding. It's right here, right? So that happens right in here, right? It looks like at 5 nights, the amount that they have to invest in their business is exactly what they make. That's the break-even point. That's where they, you know, they recover exactly their investment. And then after that, look what happens. All of a sudden, that's when you start to see what we call profit, right? They're starting to profit off of it, where their investment is staying less than what their income. This is when you start to see the money, okay? So there you go. So the answer here is after 5 nights. Or at 5 nights, right? They break even. Okay, graph the 2 equations. Where did the 2 lines intersect? So let's go ahead and graph these 2 equations that we had here. So for this one, we've got an intercept of 300. Okay, and then I can start graphing some. Let's see. So 375, that happens after 5 nights. And 450, that happens at 10 nights. So I've got 3 points that I know land nicely, and then that allows me to graph that line. So that would be, this is our costs line. Started at 300, going up $15 a night. And then when I graph this one's going to start at 0. 1 night is 75, 2 nights is 150. This one's pretty steady here, 225. And so if I graph those, and I follow that pattern, let's see, where did that intersect? Well, looky there, it intersects at the ordered pair 5, 375, right? Because that's when our income and our cost break even or are the same. Okay, and then after that, my income then goes higher than what I'm putting in, and that's where we start to see the money, like I said, right? So where do the two lines, so we graphed it, where do the two lines intersect? They intersect at 5,375. What does the point represent? It's where they break even, right? So this point represents the fact that B&B needs to rent for 5 nights to break even. At $375. Okay, and then after that they start to see the money. That's the big idea. All right, we'll finish 14 in class. So we've got 3 problems that we'll do as a quick review on Monday. Have a great weekend.